Yeah. So, is recording in order, Hanne?
Yes, it's running, so go ahead.
Yeah, very good. Thanks. Okay. So, welcome. This has a rather long title, I think, but I didn't find a way to shorten it. But I will make it clear what it is about during this webinar. So this traffic planner project, which this is concerning, is a collaboration between TOI, where I work, and the University of Bergen, where I take my PhD, as well as Epigram Image Analysis, who are experts on technical implementations of machine learning algorithms, and Statens Vegvesen, the road administration in Norway, who have a lot of data and helps us keep the relevance of the project, along with the VTI, which is the Swedish Institute of Roads and Transport. Okay, so in this talk, I will talk about the traffic planner project itself, which there are already two webinars out there that you can watch if you are interested. And then I will talk a bit about graph neural networks, which is something I use in my work, and then I will talk about my own data model, which has a working name, the toy road model, and I've never found a reason to change that name. So that's the third topic. All right, let's talk about this traffic planner project. So this text is from the website, which you can see on the bottom. Feel free to read it while I talk a bit about it. So in this project, we aim to use machine learning to do sort of efficient and fast congestion prediction based on population metrics that we know or make knowledgeable assumptions about, and some knowledge about the map structure. So in particular, we are focusing on the Oslo map, and we are focusing on populations that we have good reason to think are going to be something like what we have in 2030 and 2040. Like, they're not going to be the same as they are today, but we have made some predictions, and we'll be working with those. And this kind of analysis is already done. There is at least one good framework that we use in the project that is not machine learning based, or at least not deep learning neural network based, which is called MatSim. And this is I think we could call it state-of-the-art technology, but it's an agent-based simulation model tool where to get the congestion patterns for Oslo, we would input the entire map and all the populations, like where they live. So we generate 1.5 million agents, which each have an itinerary, and then we run everyone through the system, and congestion sort of emerges. And then we run it again, and now some of them learn from the day before where there's congestion and heavy traffic, so they will make other choices. And then after maybe 200 runs like that, we have an equilibrium, and we can tell a lot of behavioral things about traffic in Oslo if it's set up correctly. So this already works, but it requires really expert knowledge to use and set up. So our hope is to be able to make this more efficient, so that it can be done without setting up everything beforehand. You can just change some part of a road, and you will get your feedback immediately. That's our hope. So this is the goal of the traffic planner project. So this is the image I'm showing right now is the route of one particular agent in an Oslo simulation and their itinerary. So they start at home, they need to go to work, they use a particular vehicle, which is probably a car, then they need to go shopping, etc. And every day they are going to be late for some of their activities, and if that is the case, then they will change their strategy for the next day, maybe. But we make sure that not everyone changes strategy at once, because then you only get oscillating patterns. So the simulation also takes a long while to run. So it's not necessarily too long, but as I said, it requires some expert user to make use of it with a decent hardware. Okay, so now the question that we ask in this project is, if we know where everyone wants to go, which we think we do, and we know what the map looks like, which we also think we do, and we know some general traffic behavior for this area, like do people generally use cars? Where are are everyone going to the cabin on a Friday? Stuff like this. Then is it possible to predict some congestion patterns even faster than what Matsim can do? So that is our question. And we have turned to machine learning. This image was generated by DALL-E to show ChatGPT solving this problem for me. And I asked ChatGPT for if it can just do this for me, so we don't have to do the project anyway. And it was pretty confident it could give me a nice answer. I'm not that confident, so we'll take a closer look on how we can make sure that the information we get back at least is trustworthy, and that we don't sort of leave all our data in untrustworthy hands as well. Okay, so that's why we want to make this transport planner tool. Now I'm going to talk a bit about deep learning, and I will go into the specific types of deep learning that that I in particular are looking at for this project. Okay, so in old school science, there's, at least in physics, in which I have a master's degree. So this is where my example is going to be. There's historically been a trend to always try to minimize the number of variables you use. Like the fewer parameters that are in your model of reality, the better is the model. At least if it still can predict reality, sort of. So you always struggle to minimize the number of needed parameters of your model. But we are using machine learning here, and in machine learning we take a wildly different approach. Now we set up so many variables and parameters that we are sure to be to have some redundancy, and then we train it sort of on data. So we make small incremental changes so that it gets better predicting power. This is at least the thing we try to do with machine learning. So in classical physics, the researchers look at the data and make inferences. But in machine learning, we try to make the machine make the inferences. So when a machine learning system has learned something, we don't necessarily know what it has learned, but we can sort of measure the results. So this is also a risk in some ways. Like yeah, so we've been looking into robustness, etc., in the project as well, but this is not our main focus. So in the classical case, we could use Occam's razor to sort of this is this epistemological tool, I guess we could say, that is used to sort of discard any hypotheses that are more complex while explaining the same thing. So this has been used in science before, but the machine learning models are really much more complex than usual classical physics, at least. So we're sort of moving away from that as a tool. Okay, so deep learning traditionally has been done by neural networks, and neural networks, or at least the regular neural networks, which are multi-layer perceptrons. For those of you who know what that means, they are very good at dealing with data that comes in the form of tables, matrices, vectors, stuff like that. But quite recently, from 2016 and onwards, people have also been developing graph neural networks that are better suited, at least in some ways. This is the theory, at least, for data that is not easily structured as a table or as a vector. So here are some examples of that. I didn't find a very good graphic for the multi-layer perceptron, so maybe I should have started with that. But the graph neural networks, at least, usually takes a graph in some way. So you've okay, I'm going to go a bit back and forth, going back to the last slide. You could easily make a graph of this molecule, for instance, where each atom is going to be a node, and they have edges with maybe some properties, and maybe they have angles and stuff like this. And so you encode this graph, and you input it into your model, and then the model is going to have several layers, and for each layer, a new sort of intermediate graph is constructed. And so here's an example of how this intermediate graph is constructed with a one-hop neighborhood with using a graph convolutional network. So in this case, we are looking at node B, which has a feature vector which is called X, and it has an immediate neighborhood which consists of node A, C, D, and E, as we can see. So the last two nodes are at least 2 hops away from the node we are focusing on. So we are discarding those for now. And then we put the node and its neighborhood nodes into some sort of function, which can be, often it's a sum or a max or a mean function. And then we use this to construct a new vector, which is similar to the first one. Maybe sometimes it's the first one plus a new vector, which is dependent on the neighborhood. And then we construct a new graph based on this. So if the convolutional network has 4 layers, then 4 different graphs are going to be used as input, for one for each layer, usually. And then that means that if we do this twice, then for the third layer we have information all the way down from xf or xg, which were not included in the first step, will also have sort of reached our B node. So in this way, we can sort of make sure that things that are learned on a single node still know something about faraway nodes. And there are different ways to do this. And the graph convolutional network is sort of the simplest form of graph neural network. So some other notable graph neural networks are the graph attention network, which is I'm not sure if the graph attention network itself is used for ChatGPT technology, but at least the transformer, which is based on the self-attention and attention layers in the normal neural networks, is supposedly an important part of ChatGPT technology. And this GAT is the graph neural network version of the transformer. And then there's a more general kind of layer, or not layer, well, maybe, okay. A more general kind of neural network that is called a message passing neural network, which has a sort of even more general way to send these information packets between nodes. Okay, so what have GNNs been used for? In chemistry, they are used for modeling molecular structures. Pfizer made use of this for developing the COVID vaccine. In social networks, they are often used for link prediction and node classification. That means like if you have 2 friends on Facebook and they each have 2 friends, then maybe you should be friends with one of your friends' friends, right? So link prediction makes sure Facebook can always provide you with suggestions for new friends, stuff like this. This is graph neural networks very good at. And then knowledge graphs, it's used for question answering, and it is used in computer vision as well for non-Euclidean data, which means basically that it may be in an image form, but the data it's based on is really not 2-dimensional. So it which makes the distance metrics a bit off when dealing with it as a 2D object. So there have been some advances by making use of graph neural networks instead. So here's an example of non-Euclidean metrics. So in the large picture, we have our Earth, the planet, which has a spherical geometry where a triangle does not have internal angular sum of 180 degrees. while the small image, which is a zoom in sort of a single city, we have the regular kind of triangle. So when we're only using the zoomed in kind of image, then maybe we could apply a normal deep learning. But if we're working on weird geometries like the Earth here, then graph neural networks captures some of the constants and the things that we want to make sure are kept, like yeah, equivariance, yeah, and other conserved features due to the geometry, etc. Okay, so one such useful feature of or application of GNN is in DeepMind's paper about Google Maps ETA. So Google Maps has a very powerful ETA feature, which is estimated time of arrival, that can tell you about how long it will take you to get to your destination. And this paper is very interesting, and they use graph neural networks. It looks a bit like they use something like graph attention networks from the wording in the paper, but they have modified it, of course. And they have the luxury of having tons of available data, so they use data for this particular moment, like the moment they want to predict arrival time for, and they have this data for the last week and the week before and the week before that, and they have it 5 minutes before and 5 minutes before that, etc. And also a year before they know what the traffic was like, because a lot of people use their phone, and Google collects data from many of them. So they are going to know what kind of travel times are at each kind of road. And they collect all this data and use a lot of it in conjunction with graph neural networks. And then they have found this way to make sure the computation doesn't take too long. So, for instance, Los Angeles have a lot of traffic, and calculating this for every car every time someone sends a request would take too long for Google Maps service. So this is why they have made a hypergraph of the particular road segments that you want to look up, like where are you going. That makes a new supergraph, and then they can connect it to other supergraphs that they have recently calculated, and make sort of a smart this is a smart way to do it, I think. But that also means some roads in Los Angeles where people have never asked for an ETA from Google Maps, they won't have any data for those places, or at least no previous calculations to base on. So it's a sort of patchwork way to do it, but it works pretty well. And the illustration I have here is a part of the paper where they also claim to predict congestion, even better than congestion predictions based on only real-time data. So they find it's better to have access to past travel behavior here. So I think maybe I forgot to mention that earlier, but there have been a lot of advances like this one on congestion patterns. in machine learning as well. But most of them are in a couple of cases that we that aren't 100% relevant to our case. So either it's trying to be local in time, like this one. We are only interested in congestion right now, or in 5 minutes, or as you go along on your route to where you want to be. And some models successfully predicts this up to 15 minutes or 20 30 minutes into the future by using real-time data. And this has a lot of applications. And some other models can predict the congestion in maybe a city block, like a very small map, a small subpart of a town throughout the day, for instance. So it is not so local in time, but it is more local in space. So what we are trying to do in the traffic planner project is to make predictions that are that have some degree of good resolution in time, so that you can distinguish when in the day there's going to be congestion. And we also have it like city spanning, so it is not very local in space as well. So this is going to be a challenge, probably, to make sure that it doesn't scale out of hands, sort of. So we are going to need to apply maybe some similar tricks to what they did in this study. Some other application that has been very successful and is quite recent is weather prediction. So already last year there were weather predictions based on neural networks that were in many ways better than regular forecasts. Some of them were more accurate, and some of them were just faster. And some of them were better at predicting extreme weather. But now, quite recently, DeepMind came out with this learning skillful medium range global weather forecasting paper, where they use graph neural networks to great success. So this has a very efficient worldwide forecasting result, which is very interesting. And I had a look through the list of authors, and this guy is on both this paper and the last one I was talking about. So there's some learning between the papers. He also had a lot of different nice papers, so I have some reading to do after this webinar. But in this case, they have sort of made many kinds of graphs based on the surface of the Earth, which have different features that can be transmitted to the point that you're looking at. So this is a sort of more extreme version of the single super graph that was in the last paper. So I'm actually quite happy about this being a sort of progressive development. Yeah. Okay. So one of the things that makes graph neural networks, or neural networks in itself, efficient, as opposed to, for instance, MatSim that I was talking about earlier. Maybe you've heard about all the hardware that is needed for using neural networks. Most of it is used in training. So here I've constructed a little example from my own experience, where I have a sort of medium-sized task I've made some graphs and I train my neural network for 100 epochs, which is yeah, in many cases it's much, but for my networks it's at least right now it seems like a decent amount, a proper amount. But if this training takes 2 hours, then after the model has been trained, then it acts as a single function sort of. So now I only need to do it for one graph, for one epoch. So the training part is actually a very big cost in terms of the hardware costs for neural networks. And usually this kind of, at least this kind of amount of training is required to train a good model, which makes many models take more time to train than 2 hours. But they are still going to be reasonably fast in execution, usually. Yeah. Okay, so I also just wanted to mention a conference that I didn't have time to fully attend this year, but I went to it last year, and it's the Learning on Graph conference, which is hosted sort of by DeepMind, the DeepMind guys, and Pfizer. And this was, I think, the first fully digital scientific conference. So as we can see from the timetable, it's sort of US centric, but it was really neat to be able to speak with people from all over the world at once. Yeah. So if you're interested in graphs, then I recommend attending this next year. All right, so on to part 3, my own work. I got ChatGPT or Dolly to make a logo for me. This was the first logo it made with all the letters intact, sort of. So I went with it. So this is now the official logo of my data set. Okay, so the simplified road models, or the toy roads graph generator, is a dataset generator for simplified road data. It is super simplified. I wanted to make it as simple as possible while still omitting some important aspects of regular maps and regular transport behavior. To make it easy to handle now, in at least for the level I am at, it is time independent. This was an important feature for me because time is a continuous variable. So you can divide your day into 24 hours, or you can divide it into 8,000 minutes or something like this, or more if you want. So taking out the time axis is making this a lot simpler. Yeah, so I made it with a KISS principle in mind, which is the keep it simple, stupid principle, known in programming circles. And it is made for preliminary tests with the graph neural networks. So when we started doing this traffic planner project, we had access to a lot of map data and also a lot of population data, but all of it had to be cleaned and processed quite a lot before it was usable for this kind of experiment. And even then, it would be very Oslo specific. Like there isn't an average city map, I think. All cities have their own peculiarities, and neural networks are often well suited to pick up on peculiarities, and we want some results here that are very independent, or well, hopefully, if it works for Oslo, it could also work for Bergen or other cities. This would be at least an ambition for the project. So I wanted to not have static like features or patterns like a single city would have. And then by making it a graph or a generator, I can make the data sets of the sizes that I want and need. So if an experiment takes too long, then I can just scale down the data set I'm working with. Most existing data sets are that are suited for graph neural network learning, or at least that were when I started doing this, were not very well suited for our case here. So this is also a part of the motivation. And I hope that I can publish this dataset generator, or at least some of the datasets I've been using from it afterwards. Yeah, okay. So at the moment, I'm writing a paper with my supervisor about this, where I have some preliminary results from the runs, and I'm almost done with programming two different versions of the model. So I'll start with talking about the first version. I wanted to start using the graph convolutional networks, which mainly deals with data that are on the nodes. But in a normal road network, like the roads are most easily seen as the edges in the graph. So I've been working on the dual of this graph. So I made my roads into the nodes, and instead of people living on the intersections and the links having all the length, I put the length on the node, and I put all my people on the nodes. So the links or edges in my graph contain no information, which makes it easy for the graph convolutional network to handle. But it makes it a bit difficult to reason about, but not too difficult. So this is a super simple example. In practice, I use very few graphs that are below 100 nodes. But the graph is directed and it is cyclical. So I make sure that you can get from any point and back to the point itself by going through some path. So there should be one path from each node to every other node. And then they have this four features: population, the point of interest, the place where the population wants to go. They have a length, which determines if the node is part of a shortest path or not. And then they have a capacity, which in itself isn't necessarily used for the machine learning part, but I use it afterwards to determine if a node is congested or not, based on how much usage the road has. So in this model, as I told you earlier, it is time independent, which means that all transport is happening at once, sort of. And at this point, I didn't want to have the population make any kind of choice, which is maybe common. So in this model, every place with population generate traffic to every place with a point of interest. So it's a sort of transport demand pressure simulators, sort of. But yeah. anyway, it's a bit removed from reality, but that doesn't matter too much to me at the moment. So that is what the next version is for. So let me see. So these are the features. Yep. And this is how I define the shortest paths. So I generate a road usage for each node in the graph. So this is not how much the node is used, strictly speaking, but how much of this traffic pressure sort of is going through it. And if enough traffic pressure is going through it that it would reach the capacity, then I consider it congested. And so this congestion is a feature that I can test for afterwards, and this is really what I'm measuring, or what I'm interested in afterwards. So I train for road usage. I try to make it as good as possible at predicting road usage, and then I check if it can correctly identify congested nodes or not. Yeah. Okay, so before yesterday, I didn't actually make graphs from my results, and we made a small change. So this is a run I had yesterday that can show how some of the output looks for you. So as we can see, this congestion is the mean square error. That's not what you can see, but it is improving. The error in congestion is going downwards to 272, but it doesn't look like it will ever reach 0 here. And the total mean square error for the road usage is going down even more, but also never approaching 0, it seems. So when I try to look at the total accuracy of this run, so I did not divide by the total available nodes. So this should be a percentage, and will be in the next iteration, I think. But I found this graph to be very intriguing. This is an example of overlearning, and it doesn't look like the overlearning I've learned about in other neural networks. So what has happened here is that by initiating the model sort of randomly, it gets 400 nodes right first that are not congested, because it predicts that every node has 0 road usage or something like this at first. And then it starts increasing the road usage predictions. And then now at this point, there are no nodes with the nodes that it correctly predicts that are supposed to have 0 congestion. They are the first to go, it seems. So at this point, it predicts wrong for every single node, which is quite impressive. And then when it flattens out here, it predicts that every node should be congested, which is just wrong. Yeah. So I'm not too happy, but it was a very nice graph. I have done a run before that shows the total going up. So I am confident that we will get some better results. But I wanted to show you the nice graph. Okay, so now I will go on to the next version of the model. Let's call it version 1.1. in this version, we use origin destination matrix sort of. So now instead of every piece of population going to every point of interest, we now make sure that population a population has a destination and an origin. So each person starts somewhere and goes somewhere, and then that will generate the traffic. So in the first version, if there's if all the traffic comes from and goes to the edges of the graph, then all traffic will go through the central node. But in this case, we have sort of made the choice for the population. So every person is going only to one place. So this makes it much more realistic. And now road usage, since we still don't want to make a choice for the person, that is up to the agent-based simulations to do. So when there are two shortest paths, then the traffic is divided by them, between them. And we're using float numbers for road length, so this shouldn't happen too often, but this will be the case, just to make sure that we can get the same result from two equal runs. And now congestion is defined in the same way. In normal circumstances, we when the traffic is equal to the capacity and CV is equal to 1, then we have an unstable equilibrium. So it is possible that it will be congested, and it is possible that it's free flowing, and it can change sort of rapidly as far as I've come to understand. But in our case, we want the machine learning system to be able to learn something about this. So we're simplifying it to this thing. And now we've made a couple of theorems, one about mass conservation sort of, and one about incoming congestion. And we have one on outgoing congestion as well, but now we want to test these as well. So whenever some of these assumptions are fulfilled, then the conclusion of the theorem should also be fulfilled. So this is a test we're going to bake into the model, so that if we manage this, then that is even better for us than just having some accuracy metrics, we think. All right, and so I also just want to mention that for this MatSim network, the Stefan has already made a simplified Oslo network, which maybe could be a start for this supergraph techniques that I was mentioning earlier. And this is what it looks like, because the number of links here is really high for a graph neural network, I think. So we need to make use of this in a good way. All right, that's actually all I had planned to say. So now it's open for questions. We're still recording, so if you have questions but you would like them to not be on the recording, then you can just wait a little bit and then we will stop the recording. But feel free to ask some questions before that. Okay, now I think we should stop the recording, and then I'll ask again.
Okay, I'll stop it.